Caroline, do you want to put the title of the problem? Yeah, thank you. Yeah. So this is the third presentation. The speaker is Dependency Chatterjee. He's a senior ASIC verification engineer at NVIDIA. He has a master's from Stanford and a bachelor's from Jadavpur, India. He has worked at Broadcom and Intel in the past on memory subsystem, CPU, and GPUs. He has 4 papers and 5 patents. Dependency.
Hello and welcome to DBCon 2021. My name is Dependency Chatterjee. I'm a DB engineer at NVIDIA Corporation, and today's lecture will be on the mechanism to generate FIFO VC dependency graph and its application to system-level deadlock verification. This work has been done in collaboration with a couple of my colleagues, Chad Parsons and Siddhant Ali at NVIDIA Corporation. The motivation for today's presentation is to propose a deadlock verification approach which tries to overcome the challenges in the current techniques. Deadlock bugs are extremely elusive and they can often escape pre-silicon verification and emulation testing. And when they show up on silicon, it could cost the chip manufacturer millions of dollars to fix it. The current deadlock verification techniques suffer from at least one of these drawbacks in this picture. So some of these techniques, like some formal techniques, are very good at the block level, but are not scalable to the system level. There are some other techniques in formal verification, including some of the recent works, which we will see in the prior work section, which are scalable to the system level, but require very high engineering effort. There are some other simulation-based techniques which require very detailed architectural spec, but are reasonable in terms of engineering effort and scalability. And such detailed architectural spec might not be available. And then the fourth category of simulation-based testing, which are very directed and custom in nature and require a lot of human intuition. So the open question still remains, how can we develop deadlock detection techniques at low cost using a technique that's scalable to the system level and does not involve human intuition? And in this presentation, we're going to look at one such technique. So let's first understand what is a deadlock. A hardware system is said to enter a state of deadlock if it gets into a state from which there is no forward progress. So once it reaches the state, there's no set of input combination which can take it out of the state other than resetting the system. Let's now understand a deadlock with a simple example. So in the picture shown on the right, we have 2 GPUs, GPU 0 and GPU 1, and these GPUs communicate with one another over the request-response interface. So for instance, GPU 0 could send requests on the request 0 interface to GPU 1, and the read responses will come back on response 0 interface. And there is a symmetric request-response interface on the other direction from GPU 1 to GPU 0. Now, if GPU 0 is congested and says, I cannot accept responses from GPU 1, then eventually the GPU 1's internal FIFO, which stores the responses, will get full, and it will backpressure the request interface, and it will tell GPU 0, I cannot accept any more requests from you. So this request to response dependency is known and is captured in the dependency graph here, that if you block response 0, request 0 will get blocked. Due to the symmetric nature of the problem, if you block the response 1 interface, the request 1 interface will also get blocked. These two dependencies, the response 0 to request 0 and response 1 to request 1, are known. The question now becomes that if we block the request 0 interface, then can the response 1 flow freely or not? Or is there a dependency? In other words, if you block this request, can the request response coming into the GPU 0 and response flow freely? If it cannot, and if this edge exists, then due to the symmetric nature of the problem, there will be an edge from request 1 to response 0, and then we'll have a dependency in this graph. So once it enters the state where a response is blocked, 0 is blocked, and request 0 get blocked, that in turn will block the response 1, which in turn will block the requests. And basically everybody will wait for each other and nobody will make any forward progress. this is the state of deadlock. Moving on to previous work on this topic. System-level deadlock verification uses a mix of formal verification techniques as well as simulation-based verification techniques. Formal verification has been used successfully at block levels to find deadlock cases, but had some problems scaling up to system level due to the increasing complexity of exhaustively searching the state space. However, some recent approaches show that we could create some block level architectural models which are pretty lightweight, and then we could combine those block level architectural models to form a system level architectural model, and then apply formal techniques on the system level architectural model to vet for forward progress. If you're interested, there has been several papers published on this topic in 2018-19 DVCon, and the references to those have been provided in the paper. While these work very well um, at integration and system level, it suffers from the drawback that to create these block level architectural model from the RTL requires considerable engineering effort, and then you have to do the same process for all the blocks in the design. Moving on to simulation-based approaches for deadlock verification. A technique that is used very commonly is random stalling. So in the example that I explained before, in order to hit that deadlock, what we would do in random stalling is we would start stalling these interfaces one at a time and hopefully hope that the random stimulus will drive this test to a state of deadlock. While stalling does help in finding some deadlock cases, it's not sufficient. So the other approach is checking on some properties which are deadlock avoidance properties. So in this case, a deadlock avoidance property would be that if the response 0 is blocked, then the request and response 1 should flow independently. And to do that, we often write some directed tests in which we would do this directed sequence of stalling the response 0 interface, sending a lot of traffic on the request 0, and then eventually waiting for all the request 1 and response 1 to drain before releasing the stall on the response 0. And if the request 1, response 1 doesn't finish before the stall is released, then we cause the test to fail. While these kind of directed random tests do verify the deadlock avoidance properties, the problem with this approach is that you have to know the loops ahead of time, and that requires a lot of human intuition. And many of this intuition comes from prior bug escapes. The technique that I'm going to discuss in this presentation relies heavily on FIFO stalling mechanisms, and so we'll just go over the FIFO basics really quickly. FIFO is an acronym for first in, first out. FIFO is nothing but storage elements used in hardware design, and you could store a packet inside a FIFO, and sometimes also known as writing to a FIFO, or you could get the packet out of the FIFO, also called reading a FIFO. Now, FIFOs have fixed amount of storage size, and which is also known as the depth of the FIFO. Whenever the storage gets full, the FIFO cannot accept any more packet, otherwise it will cause overflow. So prevent overflow, there are two basic flow control mechanisms in which the FIFO tells that I cannot accept any more. And one of them is the valid ready protocol, the other one is the valid credit protocol. So we're going to go over the valid ready and the credit protocols very quickly. So picture here shows the valid ready protocol. In this protocol, when the transmitter wants to transmit a packet, it asserts the valid. And when space is available in the receiving FIFO, the receiver asserts the ready. When both are asserted, a packet is said to have transmitted. And when the receiver has no space, then ready is deasserted. So let's look at the waves here. What happens in here is these two clocks, valid and ready, are both high, so two packets gets transmitted. After that, the receiver gets full, so it deasserts the ready, and at this point of time, back pressure is said to have achieved. Let's now try to understand how valid credit protocols work. In valid credit protocol, the transmitter maintains a credit counter, which is a shadow copy of the internal storage of the receiver. So at the beginning, the credit counter is equal to the depth of the FIFO. When transmitter transmits a packet, it asserts the valid and it will decrease the credit count because it knows the FIFO storage will go down. When the FIFO pops out the element and more storage is available, it lets the transmitter know by returning a credit signal. So at that point of time, the transmitter will increase its credit count. In this way, the transmitter can keep transmitting packets as much as it wants until the credit count is greater than 0. The moment credit count is 0, it can no longer transmit any packet, and at that point of time, a back pressure is said to have achieved. To complicate things further, sometimes we have virtual channels in which there are multiple packets of different types or packets belonging to different credit classes are transmitted over the same physical interfaces, but we want to maintain independent flow control. So what happens in this case is that we would partition the depth in, if there are n credit classes, we will partition the depth into n regions, and the size of these n regions will be stored in n credit counters in the source. And when the source tries to transmit a packet, it first figures out which credit classes belongs to and then decrement the appropriate credit counter. And the credit return also comes with the information of which credit class this credit return happens so that the appropriate credit count can be incremented. The complete explanation of virtual channels and credit FIFOs is beyond the scope of this lecture, but I think you can still follow the rest of the presentation without having complete understanding of the virtual channels. Let's now discuss the FIFO stalling framework. NVIDIA has a tool called FIFOGen, which generates a vast majority of NVIDIA's FIFOs. So what happens is that the designers would ask this FIFOGen tool with the various set of attributes like the FIFO depth, whether the FIFO is an asynchronous or an asynchronous FIFO. And the FIFOGen tool would spit out a module, and that module needs to be just instanced and hooked up with the design. So what we do here is to modify the FIFOGen to insert pause signals, so to change the behavior of the FIFO. So for instance, for a valid ready FIFO, we will introduce one pause signal, and when the pause is deasserted, the FIFO behaves as usual. But the moment pause is asserted, and when the valid comes, what will happen is that the FIFO will deassert the ready, effectively causing a back pressure to the transmitter the moment the pause gets asserted. And for valid credit FIFOs with separate credit classes, if there are n credit classes, we introduce n pause signals, pause VC1, pause VC2 up to pause VCN. And the behavior is such that whenever pause VCN is asserted through some system verilog force command, the FIFO stops returning credit for that credit class. Moving on to stall control and monitoring sequence. Now that we have pause signal inserted in each and every FIFO of the design, what we do is we take a random test and run a special sequence on the background. And what does that special sequence do? All it does is it picks a FIFO randomly in the test, and it will assert the pause signal for that FIFO for a long time, for n cycles, and then after n minus t cycles, it will launch threads, and these threads are going to monitor the occupancy of all other FIFOs in the design. And if we find that over the last t clock cycles, the occupancy of a particular FIFO is non-decreasing and non-zero, then we will say that that FIFO is actually dependent on the paused FIFO. And we will put that FIFO in a list called LTX, where X is the paused FIFO and T is the test. To explain the situation better, let's take the example on the right, where we have two pipes containing 3 FIFOs each in linear data path, and we randomly pick FIFO F3 to be paused. And we pause the FIFO for a long duration, and after n minus t clock cycles, we launch threads to monitor all the other FIFOs. Now, if n minus t is large enough, then all the traffic that was driven in this test through the pipe B would have drained by that time, and occupancy of F3, F4, F5, F6 would be 0. But if there were some traffic which was driven into pipe B after the pause was asserted, then those cannot drain out because of the back pressure created by the pause. So in the last T cycles, we would see non-zero, non-decreasing occupancy for F1 and F2, and we'll say that LF3 is F1 and F2, which means that F1 and F2 are actually dependent on the FIFO F3. It's worth noting here that that's possible in some tests there might not be any traffic through pipe after pause assertion, and in that case the dependency list of F3 will be a null set. But if we run large number of tests, we will eventually find these dependencies and capture them in the dependency list. And also another point is, although I described this method for a valid ready FIFO, if we select a valid credit FIFO which has multiple threads or multiple credit classes, then the method is similar. Instead of asserting the pause signal, we assert the pause VCN, and then we have to monitor the occupancy at a VC level in all other FIFOs, and the rest of the method is pretty much the same. Let's move on to the final step in constructing the FIFO dependency graph, or FDG in short. To do that, what we need to do is run a large number of directed random simulations and repeat the procedure that I explained in the previous slide, so that every FIFO in the design get a chance to get stalled. And not just that, every FIFO gets stalled multiple number of times. So let us suppose the FIFO xi was stalled in ki number of times in a regression. And let's suppose that the L0xi, L1xi denote the dependency list of the FIFO xi in these tests. And as I discussed briefly earlier, that although you stall the same FIFO, it's possible that that the dependency list in the test might end up being different. And the reason being, the dependency list not just depends on the FIFO being stalled, it depends on DUT configuration, test stimulus, and so many other factors. So with the dependency lists, what we do is that we take a union of those dependency lists and then create something called a unified dependency list, LXI. So once we have the unified dependency list, the next step is to just take the stalled FIFO and start drawing edges from the stalled FIFO to every element in the dependency list. So to explain this procedure better, let's take the same example as before. In this case, we stall the FIFO F3, and let's say in a test we had no traffic through pipe A. So L1 F3 turns out to be a null set. In another test, it's possible that after FIFO F3 was stalled, a lot of traffic went in, and we found the L2 F3 to be F1 and F2. And there could be something in the middle where after F3 was stalled, some traffic went in which filled F2 but didn't overflow into F1, causing L3 F3 to be F2 only. So once we have the dependency list, we take the union of this, so LF3 becomes F1 and F2. And then the final step is to take the stalled FIFO F3 and start drawing edges from the stalled FIFO to every element in the dependency list. And then we repeat the same process for all the FIFOs in the design to create the FIFO dependency graph. Now you might think that the FIFO dependency graph looks very similar to the netlist type data path, because if we stalled F2, we'll discover the edge from F2 to F1. And then if we did a transitive reduction, we'll get rid of this edge. And then the overall graph will look similar to the netlist type data path. Well, that's partly true, but it's much more complicated than that, because in many cases, the F3 won't be a valid ready FIFO. There could be a valid credit FIFO with multiple credit classes, and we could stall a VC, and another VC in the FIFO right next to it could be flowing or independently, causing the final graph to diverge considerably from the netlist type data. Let's now discuss the properties of the FDG. Let's now take a step back and look at what we have done so far. So what we've really done is that we carried out small experiments where we stall one FIFO VC at a time in a test and observe what all FIFO VCs get stalled behind it. And by collecting this data and capturing in the form of a FIFO dependency graph, we have effectively captured all the dependency information of the FIFO VCs in a single graph. And based on that, there are several properties of the FDGs that we can discuss. And one of them is that the existence of an edge in an FDG guarantees dependency, but the absence does not. And this fact is self-evident because for every edge, you can have a change list test seed combination with which you can repro the test and look at the dependency. But the absence does not guarantee independence, and that's because it's possible that the dependency exists, but we didn't run sufficient tests or the test suite was not strong enough. But this becomes increasingly lower in chance as we run more and more tests and the test suite meets the coverage goal. The second property of the FDG is that it does not capture the temporal order of dependency. And the third and the most important property is that if a loop exists in the FDG and the edges involved are transitive, then we have a possible deadlock scenario. It's worth noting here that a cycle in the FDG is a necessary but not a sufficient condition for deadlocks. And the reason it's not sufficient is the edges of the FDGs are generated based off of separate tests. So it's possible that the edge which was revealed in one test was based on a dot configuration A, and the other edge was based off a dot configuration B, and these two dot configurations are non-overlapping or cannot happen at in the same test. So it's possible the edges in the graph are non-transitive. So a cycle does not necessarily, or it's not a sufficient condition for deadlock. But it is a necessary condition. And so by making the FDG acyclic, we kill the very necessary condition for deadlocks. So once we have the FIFO VC dependency graph, all we need to do is to check for cycles. And for that, what we do is we find the first level leaves, we mark them as level 0 and call them level 0 FIFOs. Then we remove those first level leaves and new leaves will emerge. We'll mark them as level 1 and so forth. And by recursively removing leaves, if we are left with if all the nodes disappear, then life is good. There is no cycles in the graph. And by classifying the FIFOs in different levels can give an idea about which FIFOs are the primary inputs and which FIFOs primary outputs and which are somewhere in between. And that helps in some kind of intelligent stalling, which I'm not going to get into this lecture. But if we are left with a cyclic graph, then we can deploy some DFS to automatically find out the various cycles and then basically present it to the designers. Typically, we would end up with a suspicious edge, and we have to repro that test which generated the edge and look into it. One thing to note here is that for the purpose of generating the FDG, you cannot really artificially stall a FIFO or a VC. That is architecturally not possible to be stalled. And if you do so, you might end up with some fake loops. Now, in this case, there's a way to automatically weed out such cases through a standard algorithm, which is the feedback vertex set. What this problem does is that given in a cyclic graph, it tries to remove k nodes, a minimum set of k nodes, which make the graph acyclic. And this is an NP-complete problem, so running the optimal solution for this is too hard for thousands of nodes, but there are some efficient heuristics available. So what happens is, let's say you have detected 20 loops, and then you run this feedback vertex set, and then you find by running this that by removing a set of 3 nodes, all the 20 loops are gone. Then the first question to ask yourself or the designers is that, are these 3 FIFOs really possible to be stalled architecturally? And let's say if you find out 2 of them cannot be architecturally stalled, then you just remove those 2 nodes and regenerate the graph, and maybe 19 out of 20 cycles will be gone. And then you can analyze the last 1 cycle. Moving on to the results section. This picture shows the FIFO VC dependency graph for a particular module. And in here, the red vertices are valid ready FIFOs, and the green ones are the valid credit FIFOs. This shows the same diagram for another module. And there are some of these FIFOs have no edges attached to it, and those are actually the edges which cross the module boundary, which we're not showing in this picture. So this is just a portion of the entire FDG in a specific module. We ran this FDG-based method on 3 test benches, 1 super unit test bench, including tens of blocks, and a couple of unit level test benches. And the graphs are overall several thousands of vertices. And we found some interesting loops, especially at the integration level test bench. We found a very interesting cyclic dependency between sysmember FIFO in one unit and the CPU response FIFO in another unit, which could have potentially led to a deadlock if one of the FIFOs were not oversized. But we ended up proving that that although the cyclic dependency existed, it would not deadlock. And so we carried out this process towards the end of a project, and in the coming years, we're planning to extend this to a lot of other integration test benches and do this a little bit earlier. In conclusion, I would like to say that the tool shows great promise in revealing dependencies across species, which are beyond human intuition. And it's a really low-cost method. It took us 30 days of engineering effort to develop this tool, and then porting it over across projects or test benches take less than a day. And while it has its limitation in the sense that it is only confined to the realm of FIFOs, we are planning to extend this to expand beyond FIFOs by including these kind of stalling code in other modules which have built-in flow control. So let's hope that we can use this technique to find more deadlock bugs. Thanks for listening to my presentation.
Yeah, hey, thank you, Debarshi. Yeah. So let's see, I think there is a couple of questions, looks like. Let me read out the question for you. How did you extract the DFLs, post-process the log file?
Yes, thanks, Bill, for your question. That's exactly it. So every test, we stall exactly one FIFO at a time. It's random. So we print in the log file what FIFO was stalled and what all FIFOs were found to be dependent on it. And then we have a script. So the regression log, it will just go over the regression logs and find out the DFLs for each stalled FIFO.
So that kind of leads to the next question. I mean, so were they text files or spreadsheets?
Oh, it's just the regular log files that are generated. This gets printed at the end of the log file, and we have a Perl script which processes all these log files and extract that information. Once that information is extracted, those log files can be thrown away.
Yeah, I think that kind of almost leads to the next one. I think you already mentioned, I think, how you process the graphs. I think the Perl script.
No, so these are scripts that I generated myself. There is no graph processing software. There are a couple of things that we need to do, and pretty simple, right? Finding cycles. That's you can use depth first search, and I used Avoidance to actually create those graphs for visualizations. But other than that, yeah, GraphWiz, there's some. That's the question. How did you produce the colorful graph? That is some tools generated by. I believe UC Berkeley has that. So in their website, I can give you more information on that. But the information is extracted, and then you have to put it in a specific format, and then that fancy graph generation happens. Yeah.
Okay. Yeah. I guess the next one is, what is the next step of extension for this work? Any other design elements in the data path besides FIFO?
Yeah, that's a good question, Bruce. We have been thinking about that. So any module, there are two characteristics which I would say for modules which can be extended to this other than FIFO. And one of them is that it has to have inbuilt flow control, right? And FIFOs have that, so it was ideal candidate. And the second thing is you need a way to insert these stalling code into all of those modules. And so we have to figure out what all modules are there, which are kind of ubiquitous in the design and which can be easily changed. In this case, we change the FIFO-gen script to insert it. So that's the thing, right? So that's the next step. And there's one more step, which I think is, which would be a progression from here naturally, is to get these graphs from unit levels and then hook them up at a higher level and then do cycle analysis on those. So far, we have been doing these on integration level test benches where we generate it at the integration level test benches.
Okay, I think there's one more. How did you find hung test, not deadlock related, versus FIFO deadlock? How you selected your test?
I didn't get that question. Can you repeat that question? How did you find hung test, not deadlock related, versus FIFO deadlocks? So we don't select our tests. We just run the random regression suite, and then if there are, so it's if we install a FIFO and it automatically gets into a deadlock, or any other kind of credit overflow, underflow assertion happens, those need to be debugged separately. So we have a stalling regression where we stall FIFOs, and there could be signatures coming out of those, like hung tests you're mentioning. So those need to be debugged separately. This is saying, let's say all tests pass, but we learn the dependencies, and we learn the dependency, get the graph, and see if there are any back edges or any cross dependencies across the tests. So that's what we're trying to learn here.
Okay, looks like there's maybe like one more. I mean, it's a follow-up from Bruce. Mm-hmm. Maybe to stall interfaces, is this a good aspect of extending?
Yeah, good point, Bruce. I think typically a lot of interfaces have FIFOs within the module. So you would stall the interfaces. And here, stalling one interfaces might not help totally, because there could be multiple VCs on the interfaces. And sometimes if you stall the entire interface, you might kind of get into fake loops. So you have to do the interface stalling at a VC level granularity. But yeah, FIFO there are more FIFOs probably. And stalling FIFOs kind of stall the interfaces in most cases.
Okay, maybe one more last question, since we are almost at the time limit. So are dependencies across VCs represented in the graph?
Dependence, yes. So we stall only one VC at a time, and we observe the other VCs. So the whole graph is actually VC level dependency.
Oh, okay. And there's one comment from Caroline, don't forget to vote on the presentations. So I would like to thank, all of our speakers, Dave, Ping, and Debarshi, and also our audience, being virtual. And thanks to Caroline from Conference Catalyst. Thank you all. I hope you enjoyed all these 3 papers.